Well, welcome you all to the next session of Fundamentals of Electrical Engineering by S.J.Sarkar. Now, we had discussed the equivalent circuit of a transformer, and the very same is actually drawn over here. So, what we can see there that R1, R2, they are basically the winding resistance, the primary winding and secondary winding resistance. X1, X2, they are the leakage reactance of primary and secondary. Re is the resistance representing the core loss. Xm is the magnetizing reactance. We are applying some voltage V1 here, and then V2 is actually the voltage across load, and the load is drawing I2 amount of current, and I1 amount of current is actually supplied by this source. This is ideal transformer and having the turns ratio of N1 to N2. I1 dash is a current that is drawn in the primary side, and I2 is the current, and I0 is the no load current, which is having two components, IE and IM. IE is the loss component of current, IM is the magnetizing current. So this is basically the equivalent circuit of a transformer. So from the circuit, what we can say that if I am considering the rotor element, so from that we can write E2, that should be equal to V2 plus I2 R2 plus JX2. They will not be vector, they will be scalar. So what is happening? If this point is potential positive, so this point will also be positive. Therefore we are writing E2 equal to V2 plus the drop across this. So I2 into R2 plus JX2. So this is what we are getting. Now if I am going towards the primary, we are having the transformer. So what we can write? We can write that I1 dash will be equal to N2 by N1 into I2. Why is it? Because for a transformer, the MMF in the primary and secondary side, that should be equal. Therefore, N1 into I1 dash should be equal to N2 into I2. And what we can say that E1 will be equal to N1 by N2 into E2. From the basic of the transformer, we are going to write this one. Now coming to the primary side, what we can write? We can write that the magnetizing, that a no load current I0 will be comprising of the loss component current and magnetizing current. So if I am applying KCL at this particular point, I can write this. If I am applying KCL at this particular point, what I can write? I1 should be equal to I1 dash plus I0. Now what we know? That this E1 is actually opposing the V1, and therefore generally we consider E1 as minus E1. So if that is the case, what we can write? We can write IE should be equal to minus E1 by RE, and IM will be equal to minus E1 by JXM. Now, if I am applying KVL in the inner loop of the primary, or I could say the outer loop of the primary, what we can write? We can write V1 should be equal to minus E1 plus I1 into R1 plus JX1. So this is what is going to happen. So whatever the mathematical relationship we had done, now based on this mathematical relationship, basically we are going to draw the phasor diagram. Now, to draw the phasor diagram, we need to consider something as a reference. So for the sake of simplicity, I am assuming V2 as a reference. Now instead of V2 you can take any value. In different book, different reference were taken and the phasor diagram is formed accordingly. So for the sake of simplicity, I would be starting from the output and gradually coming towards the input. Now what about I2? I2 would be basically dependent on the type of load what is being applied. Now what are the different type of load it might be? It might be resistive load. So in that case, V2 and I2 will be in phase. It might be RL load. So in that case, I2 will be lagging V2 by some angle in between 0 to 90 degree. Load may be RC load. So in that case, the I2 would be leading V2 by some angle in between 0 to 90 degree. This load can also be either pure inductive or pure capacitive. So in that case, the current would be lagging by 90 degree or leading by 90 degree. In case of a L, they would be lagging by 90. In case of a C, it would be leading by 90. So generally for our practical applications, this V2, this load is generally inductive in nature. Whatever household load we are having, they are generally inductive. So in that case, we could say that I2, I am assuming it would be lagging V2 by some angle, say phi 2. Okay. Now, this I2 is passing through R2, so there will have some voltage drop across it. Now, in case of a resistor, voltage and current should be in phase. So, therefore, the voltage drop I2 into R2, it should be in phase with I2. So, therefore, I am drawing this one parallel to this I2. The same current I2 is passing through X2. So in that case, in case of an inductor, current would be lagging. So therefore, voltage would be leading. So what is going to happen? This should be I2 into X2. Now V2 plus I2R2 plus J I2 into X2, that is what? That is basically E2. So this should be E2. Now this J, I had said that J actually implies one angle 90 degrees. So you could see V2, I2, R2, J, one angle 90, it is having some 90 degree angle and going down, going upward. So it is forming E2. Now what is given? N1 is higher, N2 is lower. So therefore E1 will be in phase with E2, but it would be of slightly higher magnitude. So this should be E1. Now corresponding to that, I would be drawing the thing in the negative direction. Almost equal magnitude I would be making. So this is suppose minus E1 we are getting. So far I was in the secondary side. So from that I would be coming towards the primary side. And by the way, this, if I'm joining, this should be I2 into Z2. That is the voltage drop across the impedance. Which impedance? This R2 plus JX2 impedance. Now we are having I2. So there we'll have some I1 dash that would be 180 degree out of phase with respect to this I2. Why? Following this relationship, I1 dash equal to N2 by N1 into I2. So N2 is lower, N1 is higher. So therefore I1 dash will have a lower magnitude than I2. Why 180 degree out of phase? Because the flux produced by I2 and I1 dash, they are opposing one another, and therefore it is assumed that they are 180 degree out of phase. Now what about E1 is here? So what about IE? That is equal to minus E1 by RE. So therefore what we can say, that IE, the current passing through the resistor, RE, that would be in phase with minus E1, and this magnetizing current would be here, because it would be minus E1 by JXM. In case of an inductor, this current will be lagging the voltage, so therefore IM would be somewhere here. And now the vector addition I would be performing. This should be IM plus IE, that would be I naught. So following which relationship? Following this relationship. Now IM is magnetizing current, so therefore the flux produced by it should be in phase with it. So therefore flux will be in phase with that of IM. And you could see that the flux is actually leading E1 and E2 by 90 degree, because there is some differential operation there. So due to which there is the 90 degree phase shift. Now I naught plus I1 dash is I1. So let us try to draw the thing. So this should be approximately the value of I1 . Now there is a voltage drop I1 R1 that should be in phase with I1. So what I am doing here, I am drawing this I1 R1. So they are in phase, they are in parallel. Then there will have a voltage drop I1 X1, voltage drop across this one. So we are drawing it in this direction. Now finally we would be joining this with this. So this should be the V1 from this relationship, minus E1 plus I1 R1 plus J I1 into X1. And if I could think of this angle between V1 and I1, this is basically the input power factor angle phi 1. So this is how basically this equivalent circuit of a transformer will be looking like. So this is the phasor diagram which we had obtained from this equivalent circuit of a transformer. So this is what for today. Thanking you. Have a nice day.